to start. So, I'm pleased to introduce Dr. Hans Christen, who's had a distinguished career as a basic research scientist and in group and division leadership positions at ORNL. Hans is the director of the Neutron Scattering Division at Oak Ridge National Laboratory. He received his PhD in physics from École Polytechnique Fédérale in Lausanne, Switzerland during 1964 for research performed at the well-known IBM Zurich Research Laboratory. After a postdoctoral appointment at ORNL, he worked on development of pulsed laser deposition equipment and scanning microwave measurements at a scientific equipment startup company. Hans joined ORNL as a staff member in 2000 to perform research in epitaxial complex oxides and led the thin films and nanostructures group from 2006 to 2013. In 2013, he became associate director of within the National Science and Technology Division. He served as an ORNL manager for the DOE Materials Science and Engineering program from 2011 to 2013. From January 2014 through August of 2018, he led the Center for Nanophase Material Sciences before taking the role of Director of Neutron Scattering Division in September of 2018. He's also a fellow of the American Physical Society. A final note, a personal note, Hans was a co-author on a couple of my scientific publications, 2007 and 2008, when collaborating across ORNL divisions. Hans graciously gold-plated some thin commercial nanocapillary targets used in heavy ion transmission experiments in the physics division that led to some fascinating, unanticipated basic scientific results. So we're pleased to welcome Hans, and thank you for coming, Hans.
All right. Well, thank you very much for the introduction and for bringing back some memories, fond memories of some somewhat distant past. I want to start by thanking the Friends of ORNL and the organizers for giving me this opportunity to share with you my passion for using neutrons to understand materials and the hidden properties of materials. Neutrons are an extraordinarily valuable tool, despite the fact, or maybe precisely because of the fact, that they are free of charge, at least in a sense of physics. They're obviously charge neutral. They are a very powerful tool to look at a number of different things, and I'm going to start here by listing just a couple of the topics that I think we all know are very important for our society, going from manufacturing to energy, to food, to medicine, and so on. I want to walk through each one of those examples and give you an idea of the types of questions that we have and for which we can use neutrons. Manufacturing obviously is an important topic, and 3D printing, a way to make different materials and produce structures that cannot be produced otherwise with very little usage of material, is really important. But understanding these structures, how they evolve after they're printed or while they're printed, is extremely important to advance those things. Converting waste heat to electricity or other forms of energy conversion is very important. Converting waste heat to electricity is a property that we call thermoelectrics, and I talk a little bit about where questions are in those materials. Drug development, I think at this time everybody understands the importance of that. To develop drugs, we need to understand the very basic properties of proteins. We need a molecular level or atomic scale level understanding of proteins in viruses, for example. Food security, and particularly in the context of climate change, is obviously an important worldwide topic, and understanding how plants respond to drought and how we can create plants that better take up water is an important aspect for a large fraction of the world's population. Plastics, issues of plastic recycling, upcycling, reuse are obviously very important, as are different uses of plastics in medicine, in electronics, and so on. And understanding the properties of polymers at a atomic scale level again is critical to develop the next generation polymer materials. Computing, quantum computing is a big topic related to computing security, to encryption, to many other applications, including quantum sensing. It requires different materials that have very unique properties that arise from effects at the atomic level, and understanding those is critical for knowing how to find the next applications in quantum computing. Batteries playing an important role everywhere, from storing renewable energy to automotive transportation, to electronics. To develop the next battery materials, we need to know how ions move within materials during battery cycling. Those are all topics that are extremely important, and I'm going to use this kind of as an outline of my presentation. I'll show you these as examples for where neutrons are being used and how neutrons are being used. I'll tell you a little bit about the unique properties of neutrons that are relevant in this context, of why these neutrons are particularly useful for that. And of course, I'll talk a little bit about the different sources we have at Oak Ridge National Lab, the High Flux Isotope Reactor, and the Spallation Neutron Source, and in the future, a second target station at the Spallation Neutron Source. So let me talk about start by talking about what a neutron is. A neutron is a particle that interacts with the nucleus in a material or in an atom. And I have a picture here of an atom with electrons orbiting around the nucleus. And this is an extremely wrong picture because the scales are way off. The ratio between the radius of the atom to the ratio of the nucleus is about 10,000. And to put this in context, 10,000 is the ratio between the length of Neyland Stadium and something an inch diameter in the middle of Neyland Stadium. I picked a spoonful of quark as an illustration, and that is simply a nerdy joke, because a nucleus, of course, consists of neutrons and protons consist of quarks, and whether you have up or down quarks determines whether it's a neutron or a proton. That gives you an idea of the scale. Now, in reality, a nucleus from the perspective of neutron scattering is a very rigid structure, so it's probably better to picture a 1-inch diameter steel ball sitting in the middle of a football stadium to give you the idea of what it actually looks like inside a material. Now, then when a neutron interacts with matter, the first thing to consider is that on that length scale and that scale of properties, every particle has to be treated as a wave. Every particle is also a wave. And that determines then how a neutron interacts with materials. And of course, we have very different kinds of materials that we encounter around us. And for each one of those materials, we use different techniques to understand their properties. If we have crystalline materials in which the atoms are arranged in periodic structures, or polycrystalline materials that have multiple orientations, as in any rocks or concrete or metals or ceramics around us, we use a technique called diffraction, where we look at the way these waves interact with atomic planes, and that gives us very precise information of where the atoms are in these structures. When we have assemblies of large molecules or of nanostructures, we use wavelengths, neutrons with a much larger wavelength, to look at small deflection of the neutron beam. We call that small angle scattering. That gives us information on the shape and the density and properties of these nanostructures within a material. This is called small angle scattering. When we look at interfaces in electronic materials, biological membranes, or particularly in batteries, we use a technique called reflectometry to look at the properties very specifically within the interface. Each of these techniques is tailored to one of the specific applications, but they all rely on the fact that a neutron is a particle. It has no charge, it does have a mass, and has a magnetic moment. because it has a mass, its wavelength relates to a certain velocity. And I have a chart here that is not very important from the specifics, but just to illustrate that the velocity of a neutron depends on its wavelength. And of course, its wavelength depends on its energy. And it just so turns out that at the energies, at the length scales that matter in many of the materials, 2.6 angstrom, an angstrom is a 10 billionth of a meter. So this is the scale typically that you encounter in materials, sort of interatomic distances. The neutron happens to have an energy that is actually also comparable to some of the energy scales that are important in materials. And I'll get back to that in a couple examples. And that is very different from what you have in photons, where the energy scales are very different. Photons and neutrons are often used as complementary techniques. They probe very different aspects of materials. And I'll show you some examples of what we can do. So when we have a beam of neutrons, what can we measure with that? Well, we can measure how many neutrons at a given energy are scattered in a certain directions. This is what we call elastic neutron scattering. And that tells us where the atoms are, or because the neutron is also a magnetic moment, where the magnetic moments within the material are. So that's diffraction, small angle scattering, and diffractometry. A neutron that goes through a material will also gain or lose energy through that interaction. And by studying how much energy a neutron gains or loses as it goes through the materials, we can deduce the things that, or the properties within the material. So it tells us actually what the atoms and what the spins are doing, not just where they are. And finally, as you shine neutrons through a material, some of them get scattered or absorbed, others go through, and that is used for neutron imaging. That gives us very specific information on composition. It turns out that the neutron cross-section, because the neutron interacts with the nucleus and not with the electronic charge, is very highly dependent on the element and sometimes even on the isotope. So on the left, you have a chart that shows the penetration depth of neutrons, X-rays, and electrons into a material. This is a log scale. So the scatter here, if you look at X-rays penetrating into the material, there is a more than 1 million change of how deep an X-ray goes into material, depending on whether it is lead or whether it is water. For neutrons, the scatter is all over the place. And so, for example, if you look at the comparison between lead and hydrogen, you can see that neutrons actually penetrate much deeper into lead than into hydrogen, which is really something fundamentally different from other probes. And it's all over the place, and which we can really use. So on the right, I have the scattering cross-section for just a few examples. X-rays, obviously, the heavier the material, the bigger the atom looks to X-rays. So manganese looks big and hydrogen or deuterium looks small, and there's no difference between different isotopes. Hydrogen or deuterium are two isotopes of the same element. Hydrogen has a nucleus consisting of 1 proton. The deuterium has a proton plus 1 neutron. They have the exact same chemical properties, but they look very different to neutrons. Lithium has different isotopes that also look very different to neutrons, where in X-rays still look the same. Manganese looks pretty small to neutrons, and so we can actually easily see lithium within a material that contains other elements. So these are critical things for neutron scattering. But let me go back to this example of lead and hydrogen. Because neutrons penetrate through lead so very well, we can do something as spectacular as putting a flower inside a lead cask and taking a neutron imaging and seeing the flower inside the lead cask. Now, question is, what can you do? What useful things can you do with that? And here's the one example that I want to show about water uptake. You can actually put a living plant with dirt in a metal enclosure in front of a neutron beam. And because water is so very absorbent to neutrons, you can see how water gets taken up into a plant after you subject the plant to drought conditions. Because you can see lithium very well, you can put a working battery on a neutron imaging beam line, and you can cycle the battery, you can charge and discharge the battery, and you can watch how these fingers, these dendrites, grow. These are the ones that result in short circuit in a battery. They're very detrimental. Usually they are studied by cycling a battery till it fails and then taking it apart and looking at where the dendrites formed. With neutron imaging, we can actually look at this happening while we charge and discharge the battery. And because neutrons penetrate deeply through a material, we can look at steel parts. These are 3D printed turbine components. These blades, they have a complex structure. They have a built-in cooling channel, as you can see here on the right side. This is a steel part of a few inches in diameter. And with neutron imaging, you can actually see the inside and determine the intactness or the quality of the cooling channels within this 3D printed component. Because neutrons penetrate deeply through a material, we can use this for other things, and particularly in diffraction, this is exciting. If you compare X-ray diffraction to neutron diffraction, X-ray diffraction is great because you can focus an X-ray beam to an extremely small volume, a very small spot, and you can do a very precise analysis of a very small part of your sample, as long as it's near the surface of the sample. Neutrons, on the other hand, will give you the average information of the entire sample because the neutrons will go through the whole sample. That is very useful because it gives you much more accurate information about many things. But we can go one step further and can use a technique called a collimator, where we basically set our detector to only look at one part within the material. So with that, we have a focus beam of a neutron coming through, and we look at one part along this path, and we look at the property of the material at that particular spot. And with that, here you have on the picture, the photograph on the right, you have a 3D printed engine component made by Honda of a very novel alloy. And the question is, what kind of mechanical stresses are built up during this 3D printing process? It's really hard to figure that out, because if you cut it apart to look at it, the stresses are no longer there. So you have to have a technique where you can measure the stresses inside the component, and neutron diffraction allows you to do just that. That helps you then to design the process for 3D printing of these materials. Now, with these very dissimilar cross sections, neutrons are very sensitive to light elements, lithium, hydrogen, as two examples. And I give you two examples here where this really matters. The top example is a battery application. And by the way, for those who are interested in specific details, for each of the examples, I indicate where the measurement was done. So this was done at the Spallation Neutron Source on the Vulcan beamline, and the one down here was a combination of SNS and HFIR instruments on two different beamlines. So it's on all of the materials, together with the citation where it's done and the logo of the institution that worked with this on this, because a lot of these things are collaborative efforts with researchers from across the world. The top example is a cycling of a battery. As you discharge and charge the battery, you have a different voltage on the battery, of course, and different things happening. And with doing the experiment while the battery is being cycled, you can determine where the lithiums move and where the lithiums go first and which parts of the structure are filled last. And this really helps then to design new materials and design structures that have the right channel structure for lithiums to move in and out. The second example is an example from superconductivity on the bottom half of the slide. These arsenic-based superconductors, they became they were discovered something like 10, 12 years ago, maybe, a really hot topic of trying to understand these. And it turns out that some of these materials are very air sensitive, and it wasn't clear why. From X-ray diffraction, you can determine where the potassium, chromium, and arsenic is in this material, but from neutron diffraction, you can also determine where hydrogen is. And there was not an intent to have hydrogen in these samples, but in the process, there was some chemical processing and some washing that actually resulted in introduction of hydrogen that wasn't seen by any other technique. And it turns out that the hydrogen actually really affects the electronic properties of the superconductor. An example that has gotten a lot of visibility in the last few years, as you can imagine, is understanding the properties of the certain proteins within the COVID virus. Here, the main protease. Understanding this at a very precise level is important, because the interaction between different proteins happens, as you would imagine, through the outermost elements. So if you have a very complex structure, there's some elements on the inside of a big squishy thing and some on the outside. It's the ones on the outside that interact with other materials, and the ones on the outside happen to be the hydrogens in almost all cases. And if you compare on the right the data from X-rays and the data from neutrons, what you see on the X-rays, you can see certain elements, but the hydrogens that are further out are entirely invisible to X-ray diffraction studies. And that really matters to understand how these proteins interact with other proteins and how they interact with drug molecules. This is the type of result that gets studied here at this beamline. It gets made available publicly, and any drug maker in the world then has access to these results coming from our studies at Oak Ridge. The fact that neutrons are sensitive differently to different isotopes, hydrogen and deuterium in particular, makes it possible to do what we call contrast matching. And that's a method to make parts of your sample invisible. So I'm giving you an illustration here of, imagine these polyacrylate beads, and you're looking for some information within those beads. That would be impossible to see until you add something to this environment that essentially makes the beads invisible. This is not removing the beads. The beads are still there, but they're now surrounded by a medium that has the same optical properties as the bead, and therefore the beads essentially become invisible to the eye. Now, obviously, we're doing something quite different with neutron scattering, but imagine that you have a polymer, which is typically a backbone, a long chain of carbon atoms with complex arms around it, and you want to understand the shape of this backbone. The way to do this is to make the side chains invisible. And you could do that by not making the side chains using hydrogen, but using deuterium, and then using different solvents to look at this. And depending on what the solvent is, whether it's water, or in this case, I think it's actually benzene, a hydrogenated benzene, the whole polymer is visible. Or you can go to deuterated solvent, the back chain is visible. And if you do that, that will tell you the shape just of the backbone. The outside has become invisible. And that leads to an understanding of what this conformation length here is and how this polymer in particular actually deforms in real situations. Another example for that is looking at the interaction between one of the protease, the TLPro protease from the SARS virus, how that interferes with a particular human gene that is responsible for the immune response. They form complexes that are big squishy things, and it's really hard to understand where, how these things deform. So the darker structure here is this, this human interference stimulated gene that typically has this shape as you see at the right. But when it binds to this protein of the virus, the way the virus interferes with that is by deforming this protein. Now, this study was done by using different molecules that were either containing hydrogen or deuterium, and then looking at in different backgrounds, so that depending on which experiment you do, you can either see the protease or the interference stimulated gene. So you can make one visible or the other visible to help us understand these particular properties. So that's about contrast matching. Now, the other thing is, neutrons are actually a magnetic probe. Each neutron has a magnetic moment. We do say that every neutron has its moment. But because neutrons have a moment, they help us determine magnetic structure. Now, magnetic structures depend on how magnetic moments within a material are ordered. And the one that we typically know as a magnet is a ferromagnet, where all of the moments point in one direction. It turns out in reality, very often they don't all point in the same direction. They form domains, some point in one direction, some point in another direction. And these domains actually have an important application in technology, and I'll get back to that in a moment. But I want to point out that there's a different example of where these moments can order in this sort of checkerboard pattern. This is called an anti-ferromagnet. And it turns out that for a long time, this was predicted from theory, but there just wasn't a way to actually determine that experimentally. And so in 1949, and I want you to remember this date, 1949, and then again in 1951, researchers Scholl and Wallen determined experimentally by looking at a particular material at different temperature that there is in fact this superstructure, this additional ordering of these magnetic moments in this anti-ferromagnetic way that really was only speculated before, and this was done early on at Oak Ridge National Lab. Now, this is one of the examples of magnetic structures. Newer studies look at much more complex magnetic structures in materials. Here's one example on the silicate material. What you see here are these complex rings of atoms and an arrangement of spins in a certain direction. These are important materials for applications, particularly sensing and communication type applications, quantum applications. Understanding how the magnets, how the magnetic moments, how the spins order in the structure is really important and very difficult. And with neutron diffraction, you can determine where they sit and which direction they point. The bottom example is going back to small angle scattering and looking at domain walls. Now, it turns out that for some applications of data storage, you want small magnetic areas. They're separated by domain walls. And there are certain techniques where you can use an electric current to move these domain walls. Understanding these domain walls and how they move is obviously important to develop these applications for data storage, and small angle scattering allows us to see how they move and thus to improve the materials for those applications. So those are the two things that I've talked about. We can measure where the atoms and the spins are. We can look at imaging. Now, I just want to say a few examples on what we call spectroscopy. How much energy does a neutron gain or lose at a given energy? Now, because atoms move, they can transfer energy to and from a neutron. So on the left is a simple sketch of a molecule. Within a molecule, you have vibrations of the atoms, and those vibrations occur at very specific frequencies. And these frequencies give a signature of a molecule. Each molecule has a very precisely defined vibration frequencies, and therefore precisely defined amount of energy that a molecule can give to a neutron or take from a neutron. On the right is an example of atomic vibrations in a solid. You can picture a solid as a bunch of atoms tied together, sort of in a spring-like fashion. And it turns out that a lot of the motions of these atoms are collective. They're what we call modes, they're phonons. Very important for understanding thermal transport. And something very similar happens with collective spin motions. If each one of these molecules or each one of these atoms has a magnetic moment, there's waves that go through this that happen in certain directions at certain energies and really help us understand these materials. The thing here is that the typical energies for these things are in the scale of tens of milli-electron volts to sort of, which is just happens to be the energy scale of neutrons. And so neutrons become a very powerful technique to observe these kinds of phenomena. So I'll give you two examples here on vibrational spectroscopy, looking at molecular motions. On the left is an example coming back to looking at some of the molecules that you've probably heard of in the media over the last 2 years, the types of proposed drugs that have come up, understanding how the little end groups here move depending on whether this molecule is in a dry or in a wet environment is something that has been possible to do using neutron scattering at different instruments. On the right is a different example on chemical separation. So this is a question of catalysis. In many applications, you have a mix of acetylene and ethylene. And for polymer production, you need to have pure ethylene. You need to separate these out. And one way of separating these out is to use one of these structures that are framework structures. So picture a large chunk of material that has these tiny little holes in it, and you put catalyst on the inside. Now, how would you know what happens inside of a material? Well, you would know that by looking at the molecular signatures, the vibration signatures, as the catalytic process is happening And by using neutrons, you can probe and you can detect intermediate molecular structures or molecules that form during the reaction while the reaction happens inside of the material. And that obviously is the type of information needed to develop better catalysts. Now, I mentioned the properties in solids. On the left is an example of a particular thermoelectric material, so one of the materials that converts heat into electricity. They have to have very specific properties on how they transport the heat. And we use neutrons to map that out and then make a very careful comparison to theoretical calculations to make sure we understand how these waves propagate through the material. On the right is the equivalent example on magnetic excitation. So what you see on the right is another spectrum that looks somewhat similar, but it's now looking at how magnetic moments collectively change within the material in a wave-like fashion. And this particular one has a very unique feature of how these two modes interact that gets physicists extremely excited because it looks like a lot of other types of things in other materials. Lets us think about ways we can use such novel materials for computing and sensing applications. All right, so those are the different things we do. We measure where the atoms are, we measure what the atoms are doing, we make images. But where do we get the neutrons? Quick detour to the history. In 1932, James Chadwick, who later got the Nobel Prize for this, wrote two papers. The first paper, The Possible Existence of a Neutron, where he had this figure here on the top, where he actually described this unknown radiation coming up off of this paraffin, of this material here, off of this beryllium, not knowing what this radiation is, and then later confirming that this actually matches all of the predictions for what the neutron should be. He used a radioactive source, an alpha emitter, that shined alpha particles onto beryllium that knocks neutrons out. And later on, it was determined that these neutrons actually act as a wave. That's the picture on the lower left. So this is how it started. This is not how we make neutrons anymore. The most efficient way, or the traditional way of producing neutrons, is by nuclear fission. You shine a neutron of a specific energy onto a uranium nucleus. The nucleus will split, it will release energy. This is what the nuclear power plant does. And in the process, it releases neutrons, which are then used to split the next uranium. And if you control this very well, you can maintain a very steady nuclear reaction. And the first place that this has been done, of course, as you all know, was at Oak Ridge, the Graphite Reactor in 1943. That was the first place where this was controlled and maintained. Now, this was in 1943. The fascinating thing is that in 1944, the reactor was already used to do neutron scattering, to show that you can use neutrons to probe the properties of material. And so on the right, you see the two people working together, Ernie Wolin and Clifford Scholl, that were also those authors on the papers on anti-ferromagnetism, not that much after this. Really groundbreaking work here at Oak Ridge very early on. Oak Ridge then had several other reactors in the course of time. There was a research reactor that was extremely impactful on neutron scattering for many years. Right now, today, we have the High Flux Isotope Reactor that was actually built in the 1960s, and it was primarily built to produce isotopes. Has very unique properties. There was another reactor built at Brookhaven that was actually optimized for neutron scattering, but was shut down much earlier. So right now, the high flux isotope reactor is here as a source for neutron scattering. It is used for isotope production. It produces a large amount of the critically needed isotopes for industry and for medical applications. It's used for irradiation studies to understand how materials behave over time in a reactor environment, but also for some other fundamental studies, activation analysis for chemical studies, or fundamental studies, fundamental physics to understand neutrons and neutrinos. This is what HFIR looks like, a reactor building with a cold guide hall. I mentioned in a moment what that actually is. An aerial view looks like this. And if I zoom out and compare this to the layout of the HFIR, there are 12 scattering instruments scattered around in what you call the beam room. So here in the center, you see the reactor core. This vessel here sits in a pool of water. And the water is used to moderate the neutrons. We call that moderate. The neutrons come off at a very high energy from the chain reaction. They bounce around in water till they have an energy that is comparable to the energy of water at room temperature. We call those thermal neutrons, and those happen to be the neutrons that have the right wavelengths to look at atomic scale studies. We also have what we call a cold source here. We shine the neutrons first through a container of liquid hydrogen. So that's at a very low temperature, and the neutrons will equilize with this and therefore have a much lower energy, much larger wavelength, and we then use that to study things at larger length scales, particularly with the small angle scattering in these large tanks here. Now, if you were to step into this, and you can actually do this, you can go to ornos.gov and look at the virtual tour. You can click around and you can see what it looks like. But if you were to walk in, you see a view kind of like this. You can tell that this is a facility that has been in operation for quite a few years. Some of these things are similar as they have been for decades. But when you look closer and when you know what's going on, each one of these instruments has continuously been upgraded and improved, providing new capabilities and continue to be improved with new things coming up. If you were to walk into the cold guide hall and you were to stand up on this bridge here across the tanks and you look further south, you see these small angle scattering tanks, you see new instruments. We're now in the newer part of the facility that was built in 2004, 2006 timeframe. Very, very active research environment. It's not the only research reactor in the world, of course. There are a bunch of others. NIST has one in Gaithersburg that's currently shut down because of a fuel element issue. In France, in Grenoble, one of the powerhouses of neutron scattering, the picture on the right here, nestled right in the Alps there in Grenoble. There's one in Japan, there's one in Australia, there's one in Munich. I do want to point out that there used to be many more reactors, but many of those have been shut down because of concerns of having reactors in urban settings. So there's a different way to produce neutrons that does not rely on a reactor, and that is called spallation. We can take a proton and shoot the proton at a heavy atom, such as mercury, and this knocks out a bunch of neutrons, and we can use those then by spallation. This is the spallation process. Here's an aerial picture of the Spallation Neutron Source. It's a large installation. I'll walk you through some of the components here. The picture here on the left, it starts with a roughly kilometer-long accelerator that accelerates a charged particle to 95% or so of the speed of light. It goes into a storage ring and it hits a mercury target. I'm going to show you a couple bigger pictures here of what the accelerator actually looks like. These are radio frequency components that operate at very precise frequencies. The many hoses that you see here are actually for cooling water to keep the temperature extremely constant. Then as you go to higher energies further down the tunnel, we have superconducting components to minimize the energy losses and to accelerate to these very high energies. The target, here's a picture with a person next to it to give you an idea of the scale. This has a continuous flow of mercury through it. It has to be a continuous flow to transport the heat out of it. It's a complex operation, but it's ultimately now a very reliable operation to produce neutrons. So the target sits in the middle of the building. There are 18 instruments arranged around that for scattering, for fundamental physics studies. If you were to walk into this, and again, you can do this on the virtual tour on the ORNL website. If you walk in, you see this big hall as you come in. The actual activity is back here in the background. So if I were to walk around to the left, what you see here is these beamlines coming at you in different directions. Or if you go a little closer to the center of it, you see this nice radial arrangement of beamlines coming out around this facility. Again, we're not the only place that does neutrons by spallation. There are other sources across the world. ICES in the UK, J-Park in Japan, and then under construction and improvement, the China Spallation Neutron Source, and also the older facility in Switzerland in Willigen. Now there are big changes happening. Europe, the European Union, partnerships with lots of countries. They are building the European Spallation Source in Sweden. That will be an absolutely fabulous source with very unique properties. They're many years out from actually getting there. We here in Oak Ridge are working on the second target station. This will use the same accelerator. We're splitting the proton beam between two different targets, and we will optimize each one of the sources for specific applications. So the second target station will be optimized for studies at larger wavelengths and broader bandwidth, so looking at hierarchical structures and things happening over time and so on. So on the right is one of the charts that kind of compares where the different sources are. It's sort of our bragging chart of showing that HFIR has the highest average brightness, and our pulse sources have some of the highest pulse brightness. Ultimately, it doesn't matter all that much. What matters is what we do with the sources and how we use the neutrons. And I hope I was able to convince you that we are taking advantage of these. It's very interesting to think about how we're using these differently. Steady state sources and pulse sources are used very differently. If you're working at a reactor, you have a polychromatic, a white beam of neutrons, multiple wavelengths, and you use a crystal, a monochromatic crystal, to select a certain wavelength out of that you shine at your sample. At a pulse beam, you use a very different technique because the velocity at which neutrons travel depends on the wavelength. If you come with a very sharp pulse, as this pulse travels to your instrument, it will spread out, and the high energy neutrons will come first, and the low energy neutrons will come later. And so we can shine all of that onto our sample and measure time of flight of when the neutrons arrive, and from there know what wavelength that neutron had. So if you do diffraction at a reactor, we come in on a monochromatic crystal, we have a sample that we arrange in there, and we put a detector there to measure what happens in a certain direction. Here's one of the examples, the diffractometer at the HFIR on the top right. At the bottom is another example of a diffractometer. We don't need to have a detector just in one place. We can have a whole bank of detectors, sort of half-round arrangement of detectors, so you can measure in multiple angles at once. This is how diffraction works on a reactor source. At a pulse source, it's very different. On the left, you have our powder diffractometer, our high-resolution instrument. The instrument is at 60 meters away from the source. That gives the beam time to the pulse to spread out. You can select a certain part of this, and the entire range of wavelengths hits your sample, and you measure at a time of flight and around it. A very efficient way to collect a lot of information for multiple wavelengths that you can then calculate back what it really means. You can have detectors arranged in certain geometries. On the right is an example of our macromolecular diffractometer, the one that has been used for a lot of these polymer studies that I mentioned. You want to capture as much as you can in different orientations, so you arrange detectors around the sample in a nearly spherical environment or arrangement to get the full information. All right, with that, I just want to finish a quick note on how we actually operate. We're part, of course, of a national lab system with user facilities. The Department of Energy operates a number of user facilities, light sources across the country, particularly in Oregon, at Brookhaven, and in California. The 2 neutron sources here and the 5 nanoscience centers scattered across the country. And the thing that is really unique, that is not replicated anywhere else in the world, is that access to these research facilities is really granted to any researcher from across the world, simply based on a scientific peer review, simply based on whether what they propose to do is important and relevant. And the researchers do not get charged for the research if they intend to publish the results in the open literature. So that's a very unique environment that makes us a very international environment, a very open environment to collaborate with people from across the world here at Oak Ridge. And so, of course, you know what Oak Ridge looked like. It all started with the Graphite Reactor here. That's now part of the main campus. The research reactor was next to it. Then the High Flux Isotope Reactor here on the south side, on the right of the picture. And now the Spallation Neutron Source up on the ridge, with the second target station being planned to come next to it. And with that, I hope I was able to give you some illustrations of what we do with neutrons, the variety of things that we can do that have a real impact on topics that are of relevance to our world and our society. We do that because of the very unique properties of neutrons, and we have the 2 different ways of doing this, either with using a reactor or a spallation source, and we have both of those options here at Oak Ridge National Lab. And with that, I hope I gave you a feel for what's going on. I'll be very happy to answer any questions.
Okay, thank you, Hans. We have a couple questions so far on the chat window. The first is, you noted many industrial applications. How many profit-seeking organizations are authors or co-authors of neutron papers?
So the direct usage by industrial partners is actually not very high. It is maybe 5% or so of our total users. But that is an understatement of the importance, largely because the way many of the industries work to get access is to provide funding to universities and to fund a student or fund a postdoc to work at a university who then does that research here. So very often we work with students or professional researchers, faculty members who have funding from a company. So it's a little hard to track that. It doesn't happen all that often that we have studies that are proprietary, but it does happen, and it is being done that a company can say, we want to use neutrons, but we do not want to publish the results. This is intellectual property that I have to keep to ourselves, in which case they will actually pay for the access at the facility. And that does happen, and that's very often work that we can't advertise, we can't publicize, we can't really say who those users were and what they were doing. But you can imagine from some of the topics what they might be. There are obviously a lot of these are very relevant to industries of many different areas.
The second question from David Fields, very exciting work, he says. Nice presentation. SNS is examining questions related to neutron lifetime, that is beam versus magnetic model. Might there be some importance of local neutron concentration? Lifetime is very long if there is a nearby proton.
So that is a very good question. So there is a neutron lifetime experiment that's happening here at Oak Ridge. What I didn't mention is that the neutron has a lifetime of roughly 15 minutes or so, and different experiments, whether the neutron is trapped in a bottle or in a beam, have given slightly different answers for reasons that are really not particularly well understood. Now, the presence, the proximity to protons, I do not think is actually a factor, because the proton beam is pretty far away from the neutron lifetime experiment. But the other local environment, the way the neutron is captured and whether or not it is in motion or in the standstill, those things do matter. That is an intense area of research. So I forgot to mention, or I didn't have time to go into details, there are several very interesting physics experiments happening here with the neutrons and also with neutrinos. As we do neutrons, we also produce neutrinos in a pulsed way that is a unique way to study fundamental interactions of materials, the way neutrons interact, the way neutrinos are captured in materials. Long term, there's an experiment being built here to measure the electric dipole moment of a neutron. Neutrons are, of course, charge neutral, but theories predict that a neutron has a very small electric dipole moment. If it didn't have an electric dipole moment, we would likely have the same amount of matter and antimatter in the universe, and we would very likely not exist. So there's a real reason to believe that there is an electric dipole moment, but nobody has yet been able to measure it, and that is work going on at the Spallation Neutron Source right now.
Okay, the Al Ekibus asked, do any groups actually pay for use of neutrons?
Yeah, I alluded to that briefly. Yes, they do, if they do not want to have their results published. It turns out to be a very small fraction of what we do. In fact, we tend to work with industry to define what part of the research they can perform here that they can publish, what part of the research is type of information that they need, but without putting it in context of why they need it is not necessarily critical intellectual property. So it doesn't happen very often, but it can be done.
Okay, we have a question from Bonnie Nestor. She says, thanks for an excellent presentation. When will the proton power upgrade at the FTS be completed?
So the proton power upgrade. So let me put this in context first. I mentioned that we have, and let me flick back here a couple slides while I talk. So the way the accelerator is built is that it can feed both the first target station and eventually the second target station. But to do that, we first need to increase the power in this proton accelerator. And that's the proton power upgrade project that is ongoing right now. It is going to be finished somewhere in summer of 2024, at which point the power of the accelerator will have increased almost doubled essentially in power, and will then be split between the two sources. So that's going on, and it's a project that is very complex, but it's on track, on schedule. Very exciting time to have more power to increase, to turn on the lights a little bit more, right, on all of our instruments. And so 2024.
Carolyn Krause asked, says great presentation. Is there any research going on at SNS and HFIR that might lead to a Nobel Prize?
If any of us knew exactly what research is going to result in a Nobel Prize, we would all be working on that. So it's a little bit hard to predict. I think if it is possible to measure the electric dipole moment of a neutron, there's not much doubt that that would result in a Nobel Prize. There's a bunch of other things that could result in a Nobel Prize that is just very hard to predict where that is going to happen. There are, very often in these large research efforts, some of the studies that ultimately end up leading towards a Nobel Prize have started with multiple different techniques. So we had a Nobel Prize for the work on lithium-ion batteries, and of course there's a lot of work that has been happening on lithium-ion batteries at ORNL. And of course, we already had a Nobel Prize for the work done at ORNL, not at SNS and HFIR, but back in the Graphite Reactor days for Clifford Scholl and Ernie Wollen's work. So we can't predict it, but there's certainly types of research going on that falls into that category.
Just a follow-up question on one part of your answer to Carolyn. Are there any dipole any neutron dipole measurements going on right now at either facility in Oak Ridge?
Well, the project is under construction right now, so it's not measuring it yet. It actually requires adding on an additional building and building up the cavities for it. So this is a project that will take several years to complete. But it will change the sensitivity as compared to other dipole moments by other similar experiments by several orders of magnitude. So it'll be a groundbreaking experiment once it's actually happening.
Great. Betty Mansfield comments, thank you, Hans. Excellent presentation about great resources at Oak Ridge. David Fields asked the question, how often or how effective is neutron scattering in determining which drugs appear most effective as antiviral agents?
No technique by itself is very effective. I think that what neutron scattering really has done is build the roadmap or the atlas that shows you what these proteins really look like. Then there's a whole lot of other work that has happened to design molecules that latch onto these. There's a big computational effort. Once you have the structure of these viruses, you can do molecular dynamics to see what kind of molecules that you know the structure of, how they would bind with those molecules. You can then down select and then you can take those to clinical trials and so on, or first to some actual experiments and then to some trials. So it's a long process, and somewhere along that very long route, neutron scattering plays a role, but it's in the end going to be very difficult to say, and here is what happened with the neutrons. And one of the ways that makes it particularly difficult to track that is when we do this research and we understand, or we analyze and determine the structure of these proteins, we publish those results. They are now available to everybody, including all drug makers. They can use those results to design drugs, to test drugs. But because we make it publicly available, we will not necessarily know to what extent it has been used in that process.
Bob Compton comments and then asks a question. IR spectroscopy sees asymmetric vibrations, and Raman spectroscopy sees symmetric vibrations. Neutron scattering sees all vibrations. Is anyone at ORNL looking at vibrations using neutrons since John Larousse has passed away?
Yes, absolutely. So I think the example that the two examples that I showed on the development of, or the dynamics of drug molecules is one of those, looking at molecular vibrations using neutrons. The one on the catalytic processes, on the acetylene-ethylene separation, is one of them. There's a number more related to hydrogen storage, or related to chemical processes in many different areas. We have a instrument, a spectrometer that's designed specifically for vibrational spectroscopy, that is really used almost exclusively for vibrational spectroscopy. So a very active area of research that includes that engages researchers from across the world, from ORNL and from other places across the world.
Okay. We have a question, another question from Al Ekabis. What organizations are your most frequent collaborators?
So our user community includes primarily, or 2/3 of our users are from US universities. Academic researchers are the largest fraction, and of those, the single largest university as far as numbers of researchers is the University of Tennessee, due to proximity and close collaborations. I think those are the key players. But it is largely it's primarily the large research universities across the country, followed by academic institutions from elsewhere, from other national labs, and from industry.
Okay, Dave Fields asked the question, perhaps there is no electric dipole moment for isolated neutron, but an induced dipole moment for nearby neutrons. Can this be measured?
I don't think there's any evidence of an induced dipole moment, and it would actually be quite difficult to induce a moment. You'd have to apply a very large electric field to a neutron that's not touching anything, so that'd be a very difficult experiment. I do not know, but I think as long as we don't have evidence that there is its own dipole moment, that's a bit removed from my understanding of particle physics.
Okay, Al Ekabis asks, is there substantial demand for beam time? Are your beam lines substantially overbooked? Which are the most popular?
We are extremely overbooked. We have a call for proposals twice a year. People request beam time, and we can grant about 1/3 of the requested beam time. So we could easily, if you had 3 times as many instruments, we would still stay completely busy. So we are very much oversubscribed, particularly now that the reactor at NIST is not running. There's some other reactors across the world that have upgrade programs that keep them down at the moment. It's very tight. And turns out it's across the entire instrument suite. Some instruments are more oversubscribed than others. It varies a little bit. Those things change with time, but some of our very high precision spectrometers, like the Cole neutron chopper spectrometer, tends to be of the most oversubscribed one, looking at some of the quantum phenomena. Often that is also depends on the length of experiments, on diffraction. We're also very oversubscribed, but the experiments are typically fairly short, so we can accommodate a lot more users than on some of the spectroscopy experiments.
Wolfgang Negley asks, what is the actual power consumption of the accelerator itself? Is the doubling of the output linearly related to the input, or is there an efficiency factor?
I don't have the actual numbers right now. Obviously, the facility does consume a significant amount of electricity. There's a lot of electrical components. There's a lot of cooling. There's a lot of refrigeration efforts, a lot of controls. There's a number of different areas that are very power hungry, and a lot of that does scale. It doesn't scale linear with the power. So when we double, we will not, the power will not quite double the utility bill, but it will go up significantly. Not linearly, because some of the components, the cooling and the background and all that stays the same. So it relates, but it's not linear.
Okay, Carolyn Krause asked, Hans, you were a director of CNMS. Which nanoscience and nanotechnology discoveries made their most impressed you?
Where should I start? That is a tough one. Nanoscience is such a broad area with such a wide diversity of techniques and approaches. I think it is striking to anybody coming from the outside of just how powerful our tools are to understand what happens at the nanoscale, how we can actually see and position an individual atom, put an atom exactly where we want it. That's a really unique thing that is relevant and important. There are ways of synthesizing materials in very precise layered structures, materials that wouldn't otherwise exist in nature that are formed at the nanoscale. It's almost impossible to say which one is the most exciting. It's such a broad spectrum of things.
John Rather asks, very exciting, Hans, can neutrons lead to R&D progress toward room temperature superconductivity and Bose-Einstein condensates?
I think the race towards room temperature superconductivity is such a complex one that without the knowledge that we already have from neutrons, it wouldn't be possible to make the advances in superconductivity that we already have right now. So I think on the path to creating new materials and understanding new materials, neutrons have already played an incredibly important role. Whether a neutron study itself is going to be the determining factor, again, is very hard to predict. I think what happens is neutrons really help us understand the very fundamental phenomena, which then can be used in a creative way to create new materials. And so that is a whole different, a broad spectrum. It's hard to predict. It really is impossible to predict.
Al Shambliss asks, did you say U-238 or U-235 is bombarded with neutrons as a source of neutrons in your talk? No, I believe the answer is if the target is Mercury. Is that correct?
So at the HFIR side, so on the spallation side, the thing can either be mercury or tungsten or any other heavy element. On the fission side, and if I can get to the right slide here somewhere, it is uranium-238 that is used in the controlled chain reactions. in reactors across the world.
Okay, Paul Leiby asks, that was astonishing in its breadth and in informativeness. A valuable resource that is cost-free will often be oversubscribed. Can you say something about the peer review process for resource allocation? How, for example, can trade-offs be made between more basic science and industrially or socially valuable applied work and national security work?
So there are things that are scientifically very exciting, and there are some things that are incredibly important, but it might not be as easy to get people excited about it from a scientific perspective. We have to consider that. One of the key factors that we have in the peer review process is that we ask the reviewers to determine whether this is something that really can only be done with neutrons. And if there is any way to do it with another technique, we encourage people to use another technique because we are so oversubscribed. So there are a lot of things that can be done with X-rays or with microscopy or other techniques, and those are the ones we do not want to use the neutrons for. The balance between how cool it is versus how important it is I guess up to reviewers, and that's a very qualitative thing. We do ask people on the impact of the research. That's one of the factors to evaluate proposals on. And so something that is interesting but not very relevant, and something that is more straightforward but has a huge impact, they both stand a chance. We have some way to influence that by allocation. And we often make additional beam time available to industrial programs that wouldn't otherwise get beam time. National security programs often actually access facilities by paying for them, not by open peer review, because they can't discuss what needs to be done. So that's slightly different.
Okay, Wolf Negley asks, are all the experiments pre-programmed and executed automatically, or can and are some manipulated by the researcher in real time?
The vast majority of the experiments are manipulated by the researchers in real time. And this is when you find researchers at the beamline at 2 o'clock in the morning changing parameters based on the result that they got earlier in the evening. It's really an interactive way. There are some experiments. Determining a protein structure is a very slow process. You put the sample on the beam and you wait till you have enough statistics to deduce the results. Other experiments, you change the temperature, you change the pressure, you change the orientation. It's a constant interaction between the researcher and the instrumentation. So it's a very active engagement. It's not programmed in most cases.
Okay, Betty Mansfield asks, if you had unlimited resources, what upgrades or modifications would you and others and you and users like to have?
So we have a wish list, and it's not a short wish list. There are certain things. I have to say we have made great progress in changing some of the level of automation, remote access to the facility, more computing control of things that we want to go further with. Those are important. The big limitation right now is that we simply do not have enough beamlines for the researchers. We have lots of ideas for new instruments that we would like to build. Constructing a new scattering instrument is typically an expense of anywhere between 10 million and 30 million or so. So these are big things that every time you do that, obviously you increase the range by which neutrons can impact the societal needs that we address here. So that is the big thing. Now we have things that are really important to us. Obviously, the second target station will double the number of instruments we have at the Spallation Neutron Source. So that will be a huge impact. We're also working on extending the life of the reactor. The reactor is built in a way that the pressure vessel has a finite life. At some point, that needs to be replaced. That is a real big deal. That will, you know, with that, if that can be done, then we can extend the life of the reactor to the end of the century. We can add an additional guide hall at High Flux to move new instruments in and do more there. So there's lots of opportunities. I think there are lots of opportunities in what we do with the samples, different sample environments, increasing the pressure, increasing magnetic fields, working at higher magnetic fields. And there are lots of new opportunities of what we do with the data at the end. A lot of the interpretation of the results depends on a link to modeling. And right now, for many of the users, that connection of doing the neutron scattering and simultaneously doing the high performance computing is just not there yet. It's not sufficiently easy for a large number of users to take advantage of this. And so that is a limitation that a closer integration with computing would certainly be very helpful. And we're working in all of those directions, but it takes time and money.
Yes. Paul Leiby makes a question. I'm not sure I understand it. SNS plus HPC plus data science equals what?
Okay, so I think that's an interesting point. Adding the data science there. So I just hinted at the importance of high performance computing, HPC, to connect to the data that we have to extract the full information. It is quite likely that there's information hidden in our results that we haven't fully extracted, and because we don't have enough of the computational resources to do that. There are changes in how data is being analyzed by drawing parallels between different experiments and finding trends in multiple experiments. So that's the data science part that is gaining momentum. That will also have a big impact. So Paul, you're absolutely right. Adding data science to that is a key component.
And from myself, I'm wondering, just as a follow-up, a lot of the computational work perhaps is done by outside users. Is that correct? That is correct. Yes. Yes. Okay, and it'd be good once you have a better connection between your program and Frontier and so forth. That would be a real right. We're working on a compute infrastructure that actually allows users to connect their computational codes to our facilities, so that the codes that they develop can be used by a broader range of users, and we essentially act as the interface between different users who want to use computational methods to understand their results. Well, we've exceeded what we said when we said we would shut it down, but it was so interesting. I just kept it going. For your own information, Hans, we had 55 people at this meeting at the peak, and of course we had some very interesting questions and very good answers. So let's thank the speaker for his very enlightening talk. It's a pleasure to be here. Thank you very much. And so we hope to see the rest of you at our next month when Brooks talks about the East Poplar Creek. So thank you for all coming, and good day. Thank you. Bye-bye. Bye.